Alright, y'all, today we're going to look at some special right triangles. Why are they special, you might ask? Well, they just come up pretty frequently, so we deal with them enough that we've determined we can make it a point to remember them a little bit better than some of the other triangles we deal with. So, the first one is going to be what we call a 45-45-90 right triangle. I'm drawing them to scale as best I can. What we know about this is that, of course, this angle is always going to be 90 degrees. That's what makes it a right triangle. And then each of the inner angles is 45 degrees. Now, what we know about this is that each leg will denote with x, and the side length of our hypotenuse will be x times the square root of 2. Our second special right triangle is the 30-60-90 right triangle. Which again has a 90-degree angle. That's what makes it a right triangle. This top angle will be 30 degrees, and this bottom right will be 60 degrees. Now the side lengths on this one, the leg opposite the 30-degree angle will be x, the hypotenuse will be 2x, and the leg opposite the 60-degree angle will be x times the square root of 3. Now we will move on to some quick proofs of each of these, and we will understand better how we got these formulas. When we look at our right triangle, our 45-45-90 right triangle, which this is nowhere near drawn to scale, but we know based on the base angles theorem that this is an isosceles triangle, and therefore each of the side lengths opposite of these congruent angles is going to be congruent. So if we're just going to choose to denote one leg as x, well, therefore we can say the other leg must also be x. Well, we just recently have proven the Pythagorean theorem, so this is a tool we're going to use to find what this hypotenuse must be. And this is how we will prove our formula for the 45-45-90 triangle. So we have one leg squared, x squared, plus our other leg squared, x squared, is going to equal the hypotenuse squared. So we have x squared plus x squared. That gives us 2 times x squared. That is equal to our unknown side squared. Now we will take the square root of both sides to get rid of our squares, but we have to square root the entire side, not just the variable terms. And that's going to leave us with, that's going to leave us with the square root of 2 times just x is equal to our unknown. Okay, and just for convention, it makes it a little bit easier to write it as x times square root of 2 equals that unknown side, and therefore up here we know it is x times square root of 2, which is what we had written down earlier. Okay, now let's do a similar proof of the 30-60-90 triangle. Okay, let us consider an equilateral triangle. Okay, and again, this probably will not be drawn perfectly to scale, but this is an equilateral triangle. Okay, so we know that each of the angles is 60 degrees. Okay, so let's write that down there. If we drop a line right here that bisects the opposite side, we know it creates a right angle, and it also bisects this angle up here. So this angle becomes 30 degrees. Okay, that angle there. So, say that we also know that since this bisected this side, if I denote this distance here as x, then it is half of a side length, and because it's an equilateral triangle, that means that this length over here must be 2x, because it's twice as long as this half. Okay, so we're going to use that knowledge to focus on just a drawing of an equilateral triangle. Okay, so we're going to say we have this here, and it is going to be what we work with. So we have 30, 60, and of course 90. Now, like I said, we're going to note this side as x and this side is 2x. So now we need to find what this other leg is. Okay, so this is our question mark. So similar to how we did the last one, we're going to set this up as a Pythagorean theorem using a question mark as the variable for our unknown sign. So we have the first leg, which is x squared, plus the second leg, which we don't know, it's our unknown, our question mark squared, is equal to the hypotenuse, which is 2x, and that is also squared. That's the Pythagorean theorem application. So now we're simply left with x squared plus question mark squared is equal to 4x squared. Now we subtract an x from each side, and we're left with the square root, or the question mark squared, equals 3x squared. Therefore, I'm going to draw an arrow so we can have more space. Now we take the square root of both sides, and we know that the square root of a question mark, excuse me, that just the question mark will be equal to the square root of 3 times x. And that is what we were looking for, was the question mark. So now we can say that this side length up here will be x times the square root of 3 for better convention, which is exactly what we had in our original. So that is quick little short proofs of the special right triangles.